Hello, everybody. I hope everyone's having a wonderful day. So I'm sorry about the delay there. Hopefully there aren't going to be too many technical issues as we do this. So this is also the first time I'm doing this on this channel. So hopefully I'm going to work out some of the kinks that I'm doing with this stuff as we go along. Okay. So first, a couple things I want to point out. I apologize in advance. For some reason the autofocus on my camera was not working properly. So if this looks a little bit blurry or anything in this, I'd recommend checking out the written notes that I'm going to post up later on Patreon or Subscribestar should you be interested in that. But I'll talk more about that in one moment. So other than that, we're going to get started here shortly. Do note that I can't see what everybody's saying. I fortunately have a magical tablet here. It's going to be much more advanced than the kind of tech I'm going to be using in this stream. So we're going to have some fun here. Before we get started, I think I should introduce myself. So my name is Dr. Daniel Page. You can just call me Dan or Daniel. I'm not too terribly worried about that. So you might know me. I'm a theoretical computer scientist and a science educator. And here on this channel, I'll be doing, well, at least my big mission is to provide free or accessible computer science education. So what does that mean? That means that I'm going to be trying my best to make education that would normally be fairly inaccessible, more accessible here on places like YouTube. So my hope is, because this is the only one of the only things I'm doing right now, I'm kind of academically homeless as we speak. So I'm hoping that you can contribute on my Patreon or my Subscribestar if you really like what I'm doing. I'm going to be making more things available on those platforms. For example, if you've been following my data structures and algorithms, my advanced data structures series, I'm going to be making that full set of lecture notes available. So if you've been following those videos and you've been wanting to have a written companion to go along with those videos, that will be available hopefully sometime pretty soon. I'm just waiting on a couple more things. But later today, I'm going to be making those things available for this big old bootcamp, which is why we're here, right? So anyways, let's get started here. So let's just see what everybody's saying. Yes, the fun is going to begin. So let's get started. So for anybody that is not acquainted with what Big O is, I want to give you some intuition before we get started. So for some of you, Big O might be something you're familiar with or have used it before. So some of you might find some of the things I'm going to say for the next little while be like, yeah, I already know that. Get to the point. So the big thing you want to get into the habit of thinking about is if I give you a function. Now, the way I like to think of functions very often is like a machine. So imagine I have a machine and it takes an input and it produces output. So if I have my function is called f, it has an input, we'll call it n. It produces output, it's f of n. So we're going to be talking a lot about functions here. So I'm going to make some assumptions about your background. So for example, I want you to be, if you're pretty used to this idea where I have input, I feed it to some function, it produces a number. You might be familiar with that. That's cool. We're going to be talking a lot about functions. So I'm going to rely on your understanding of knowing what a function is. And also I'm going to use some basic algebra. So just keep that in mind. So what we're going to be interested in are so-called asymptotics. So what we're going to be interested in are functions when that input n gets large. What does that mean? That means that, so I'll give you a better intuition for this in a moment, but instead of thinking of numbers like n is equal to 1, n is equal to 2, n equal to 3, think about things as n gets so big that you could not imagine it, or you can just think of larger values like n is equal to 10,000. Whatever is sufficiently big enough to be calling it large. So just for those that want to get an idea where we're going to be going with this stuff. So first off, this bootcamp that I'm going to be talking about here, this is not about analysis of algorithms. This is just a piece of that. So what do I mean by that? I'm going to draw you a fun picture so you can understand where exactly we're talking about. So if you're wondering about big O here, I'm going to be talking about within the context of computer science. So oftentimes when we study problems in computer science, there's kind of some steps that you go through. So like the first step that normally people do is they present some algorithm. So now obviously they present an algorithm. Now this algorithm might be correct, it may be incorrect. The point is that somebody put a lot of thought into this and they're saying, hey, look, now I want to analyze this thing. So what am I going to do? Well, I would like to analyze this. Now, normally in the purview of computer science, we're interested in so-called complexity, which I'll define in a moment, where what we want to do is we want to measure the complexity of an algorithm. Now, this isn't with respect to a resource. So complexity, when I use the word complexity, I want you to think it's the amount of computational resources an algorithm uses. I guess that before I get to anything, I got to tell you what an algorithm is. Now, I'm not going to be going too deep on this, but usually the practical definition I like to use is that an algorithm is an unambiguous step-by-step procedure that takes input and produces output. So unambiguous in the sense that my algorithm is clearly defined such that I cannot confuse my audience, so that they can follow the steps of my algorithm to sufficient ability to carry it out. So, what do I mean by that? I give you some steps. Somebody has to be able to follow them without being confused or you misleading them. So, what do I mean by this resources? So, oftentimes what people in algorithms are interested in are time. So, this is the amount of time in terms of a number of operations. Or, so for example, when I talk about operations, I'm talking about things like arithmetic operations. I'm talking about things like conditional statements. I'm talking about comparisons like less than or equal, greater than or equal, equals. I'm talking about operations that are so-called primitive or simple. So that's the technical jargon way of saying if I take like the most atomic pieces of what I'm doing with my computer, which usually are logical operations or arithmetic operations, these all are assumed to be an operation, and we count these when we count and analyze for an algorithm. So this is the number of operations, or the so-called number of steps that the algorithm takes, which is sometimes rather difficult to analyze unless you use a type of analysis. So another one that people tend to be interested in is so-called space. So think of like the amount of memory you might use. So back to time, normally when we talk about complexity, we measure it with respect to some kind of analysis, because otherwise if we just don't pin anything down, we might be talking about different kinds of problems with different cases where the algorithm does different stuff. And that makes it very difficult to measure how efficient an algorithm is, because normally when we want to solve a problem, we want to solve it efficiently, right? So that naturally brings me to step 2. So normally when computer scientists do this kind of stuff, they decide on a type of analysis. So you might know this as, say, worst case, or perhaps there's another case called average case. And there's other things like best case. There's other kinds of analyses out there like amortized. The point is that you give me some algorithm. I'm going to decide on a type of analysis. This analysis is dictated by what I think is interesting about the algorithm. So, like I said, for those that are more computer science literate, this is going to be fairly familiar for you. You're probably just wanting to get me to all the big O stuff, which I'm going to be getting to in a moment. I just really want to frame this so everybody understands why you would want to do what we're doing. So naturally, once you've done this, you do a type of analysis and you count these operations, the things I talked about just here. And what happens? You derive a complexity function. So the complexity function, as the name suggests, measures the complexity. So whatever complexity you're looking at with respect to the kind of analysis you use. So in step 3, you derive a complexity function. So this comes from the analysis. And when you measure these operations, it's usually with respect to a given model of computation. Now, in the most technical way, for those that are watching this and they're like, hey, what kind of model are you using? It's the RAM model is pretty standard, but it really depends on the kind of machine you're talking about. But typically, the RAM model is the standard one when you talk about basic sequential algorithms. It's the one that is like the gold standard in algorithms. But there's a lot of variants of the RAM model. But I'm not going to talk about that here. Remember, we're not going that deep here. We're going to be talking about big O. I don't want to give you the whole python of algorithms analysis here. That's best reserved for another video. Naturally, the final step of this process is to determine its asymptotic. Remember, that means as it gets big, it's asymptotic behavior. So what's its? I like to be unambiguous when I describe things. I'm referring to the complexity function. And once you derive this is normally talked about as computing the complexity of the algorithm. So this action that I've just described here. So somebody asks you to compute the time complexity or the space complexity of an algorithm. They're asking you to go through this process. The part that we're going to be interested in here at the Big O Bootcamp is really just this part right here. The arrow from once I've derived the complexity function, now I determine the asymptotic behavior. So you give me some complexity function, and my job is to determine its asymptotic behavior. We're going to look at this in terms of big O. Remember, I told you big O is about measuring the asymptotic behavior of a function. There's several different interpretations of how you can look at this with respect to algorithm analysis and different perspectives. So, for example, if you're looking at asymptotics in terms of just general functions, you might have some other way of interpreting how these big O's that we're going to be talking about. I promise these are not like SpaghettiOs. We're going to be talking about how exactly we use big O to capture things like this. I'll give you one interpretation of how you use the big O to talk about algorithm analysis, but also just generally what kind of reasons why you'd look at this thing. So hopefully everybody understands this. So this is just the general gist. So if you're just lounging back listening to Dan just ramble about things, that's fine. If you're not sure what I've just been describing here, just remember, I'm just giving you kind of like the workflow of how you would analyze an algorithm. So from your perspective, all you have to think about is that we're given some function. Remember, just think of that machine that takes in inputs and produces output. I want to know how it behaves when the inputs get large. But what is that going to represent in terms of the algorithms? We'll talk about that in a moment. So very good. So it seems like everybody's having a good time so far. It's worth noting that, like I said, if say you're having difficulty reading anything here, just let me know. Just type it in the chat. Or something is unclear, just let me know. I'll try my best to address it. Like I said again, I said at the beginning, if you find yourself really wanting written notes, like the ones I have here, these ones I'll have available later today on Patreon or Subscribestar. So if you just make a contribution of a certain level, I haven't fully decided on what threshold, I'll make this accessible to you. But that'll also come with other perks too, like I mentioned. There's some notes for my lecture series, that 33-part lecture series I'm doing right now for advanced data structures that's on the channel. Look out for 3 videos, by the way, next week. They're coming. So anyways, I talked about the idea of having some function, and I would like to measure this. So oftentimes, we want to have the notion of a complexity function. Now remember, I told you what a complexity function basically is. Now sometimes people call this a growth function because naturally asymptotics, we're interested in the growth rate. So that's another way you can interpret what we're doing here. I'll usually refer to it as a complexity function because I'm a computer scientist. I'm not really looking at growth rates in other settings. I'm just looking at the complexity in terms of resources. So I'm going to write it down somewhat more technically, and then I'm going to break it down in some simple terms. I just have to get all these definitions out of the way because otherwise we don't have all the toys we can play with when we do everything in our examples. I just want to make sure everybody's on the same footing. So a complexity function is a function f on the domain of positive integers to non-negative real numbers. So if you really want the formal way of writing this down, I'm saying the function's called f. This colon signifies I'm going to perform a mapping. I'll draw a picture in a moment of what this means. It's going to take in a positive integer. So this is a blackboard Z or zeta. Actually not Z, it's Z. This represents the set of all integers. But if I put a positive sign in front on the top like this means positive. So I'm talking about numbers like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Your typical counting numbers. I'm not going to consider when the input is 0. I'm only going to consider when it's 1, 2, 3, or above. So I've given some positive integer, and I'm going to get out of my machine some non-negative real number. Now, you might naturally ask, well, Dan, what is a real number? Now, I'm not going to go overly formal on what a real number is. For your purposes, just think of your decimal numbers, which technically are all rationals. But this also captures the so-called irrational numbers as well. So just this is a blackboard R, represents the set of all real numbers. This greater than or equal to 0, I'm just using to indicate that it's not negative. So it can be allowed to be 0 or it could be positive. So I get some integer, I produce out a real number. So remember, just think of my machine. I put in a number like 1. I can get out a number like 1/2. So this is what f is. So the domain dictates what exactly goes into the machine. And then what f of the input, f of n, for example, if n was the input, that would be this non-negative real number. Are all non-negative real numbers positive integers? Yes. Yes, they are. But I'm just keeping this just to be very broad and simple. Now, if you're very much of a stickler like me, you might naturally look at this and say, Dan, why are you allowing 0 to come out of this function? Well, think about it. I'm just going to do this out of convenience because some of the functions that we'll be dealing with can output 0. However, in a realistic computational sense, it would not make sense to include 0 in here and just make it so it's the set of positive real numbers. Can you think of why? Well, remember, I told you that an algorithm is an unambiguous step-by-step procedure that takes an input and produces output. Now, naturally, an algorithm has to perform at least one operation. It's terminating condition, right? So any algorithm I give you must have strictly, it has to have something that is a positive integer as the number of steps it performs. At least if you look at its overall running time. But like I said, I'm just doing this out of convenience. If you're a bunch of stickler like I am, you might be saying, hey, look, just make this the set of all positive real numbers. But you'll see why I do this anyway. So the easy way of getting around this issue is just adding 1 to any function that produces 0, which is naturally what you run into when you do analysis of algorithms. But like I said, this is not about analysis of algorithms. We're going to take and look specifically at the part where we're analyzing the complexity function that I get. Okay? Does everybody understand this definition? So all I'm saying, okay. Okay, good. Okay. So there are several ways of talking about asymptotics without restricting things just to general functions. You'll notice that I've restricted the functions to ones that are defined on ones that look like this. So it takes in a positive integer, it produces some non-negative real number, right? Now, I'm going to just assume that I'm going to consider functions that are defined over this. So for example, if I give you a function like a logarithmic function, I'll just assume that the inputs are only going to be positive integers. I'm not going to consider any other cases with the logarithmic functions. I'll talk about logs later on. So if you're not sure what a logarithm is, we're going to talk about that. But the point is that we're going to define them on these terms. Okay. So the reason, actually, I should mention why that's really important. Some people, when they talk about growth functions, they talk about them with just any arbitrary function. I'm assuming that they're talking about computable functions, but we're not going to go into those details. The point is that they will oftentimes just say, okay, the function's allowed to produce negative outputs. So for example, if I give you a trigonometric function, something like sine or cosine, there's a possibility it can output a negative number. What normally they do to get around this is they introduce absolute value signs that turn eliminate the negative sign. So if you're looking at something like Wikipedia or something like that, they may use the absolute value sign. So for your purposes, just assume that the functions look like this. And if you really want to play around with the negative ones, ones that are allowed to have negative outputs, just put absolute value in wherever I'm going to be putting in any relation between the functions. Hopefully that's clear for everybody. That's just a technical note. So I'm going to talk about complexity with respect to this definition. So now I can finally talk about what big O is. Let's talk about big O, because I needed to talk a little bit about this. So for those that have just been sitting here and just like, hey Dan, let's get to the point. Let's talk about what big O is. So I'm going to talk about the definition. So I'm going to give you the formal definition of big O. And then what I'm going to do is I'm going to talk about different ways you can use big O. So I'll give you a couple different ways of writing it in terms of formal notation and how people tend to use that notation. And then we're going to move into the examples. So you might naturally ask, what is big O? I don't even know why I'm even holding this. If you're wondering, the dogs are barking upstairs. If you only hear any random noises, it's just because we're, like I said, this is literally a shoestring budget studio. So hopefully we're gonna have a good time here. So let's get started here. So what's big O? So oftentimes, if you talk about big O, it's signified with literally a big O. Some people call this Landau symbol. It was developed in the late 1900s, if my memory serves me correctly. Like I said, it was originally designed to talk about asymptotics. When the input grows large of a function, how does that function behave? So I'll talk more formally what that means. Like, what does it mean to behave? How does the machine that I have, like my function, how does that behave? I'll talk about that in a moment. So this came up in the early 20th century. So here's the way that we're going to talk about this definition. So I'm going to let f and g, so these are going to be names for my functions, be complexity functions. So these are going to be my two names for functions. Remember, if I write f of n, this means this is the value given n for this function. But sometimes informally people will write f of n as if they're stating the name of the function with prescribing its input. So if you see me write f of n and I'm not literally meaning the output of the function, I might be just literally saying this is just the name of the function and I'm defining the inputs for you. So for example, this is a function that's saying its name is f and its input is n. It's just a shorthand, but it's a very common mathematical abuse of notation. So some people use this. I'll use it sometimes if it's convenient. So just be aware of that. So remember, these are the names of the functions. This is the input, and f of n as a whole is technically its output. However, some people write it formally like that, just so that it's a shorthand to just say what the input is. Okay, so now I have f and g. These are just two functions. Now I'm going to write f is big O of g if and only if. Now, I like to use sometimes fancy symbols, but I have to explain what those fancy symbols mean. So I'm using a double arrow here. This represents if and only if. You might know this is a biconditional. So what I'm going to say is that this is what I'm going to define big O as. So if f is big O of g, then this definition has to be true. Likewise, if this is not true on this side, it is not big O of g. So that's just a little bit of logic I just want to point out. So if you see me use this, I'm just writing two equivalent statements, at least when it comes to logic. Okay, so let's talk about this. So, what am I going to say? Now, I'm going to write it just in words, and I'll write down the more symbolic way of writing it down, okay? Because I want to keep things simple here. If and only if there exists constants C, which this is going to be a positive real number. So this is things like 1/2, 1, 2, 5, but will not be 0. Likewise, it cannot be negative. And n 0, so n with a subscript 0, this is going to be a positive integer. So there's going to exist these two constants. These are going to play a role in how we're going to prove big O statements to be true. So just keep that in mind. So there exist these two constants such that for all n greater or equal to n0, I'm going to assume that, now remember, what proceeds after this has to be true for all n that are going to be bigger than or equal to my other constant n0. You're going to get familiar with this as we do more examples. Now I'm going to assume that f of n is less than or equal to c times g of n. So this is the formal definition of big O, believe it or not. Now, if I want to write this more symbolically, let me write it down symbolically in one moment. So just remember, I just want to break this down in simpler terms. So the rules that you have to play are you're going to find me C and N0, and they must be true such that, so if I pick these two, remember, I'm not saying that you give me any arbitrary constant. I'm just saying you pick me one C and one N0. They just have to exist. I don't need to worry about picking a C, then I have to figure out what N0 is for any possible N0. It's just that one N0 has to exist, and vice versa. Such that when I pick these two constants, this statement must hold. So this inequality must hold no matter what n is, as long as n is bigger than or equal to n0. So just to illustrate what I mean by this, I'm just going to draw out a plot. I'm going to use two functions just to illustrate this. I'll first use a linear function. So say, for example, this is f. And g, for example, is a quadratic function. That's actually quite good. I did a pretty good job on that. Usually mine are a little bit crooked. So let's so this is g, and I'm going to just assume that that these are my two functions. I want to put it in the context of our definitions. Now, the way it works is I would like to show that f is big O of g. So what's c and what's n0? Well, I pick a c such that I can find an appropriate point, or any point along here past where the two functions intersect, assuming they even do intersect. That might be possible that, I should maybe plot this out, that's n right there. So as n grows, as I make n bigger, I want to find any point after this fact. So this would be n0, and n0 can be any value that follows after this point, assuming that I pick some function that is c times g. So what do I mean by this? Let me put it in simpler terms. So if I put f of n is equal to n, and if I have something like, if I make g of n squared, if I just pick c to be equal to 1, naturally you can find the n0 by identifying where these two functions intersect. You can just solve for an equation, and you can figure out what n0 is. Now, if you're curious more about using root finding approaches, that is a valid way of determining n0. You can do that. However, you oftentimes have to make assumptions about what you know about those functions. So I'm going to avoid doing that here. However, it's perfectly valid if you just need something that works really quickly and you have an understanding of how the functions behave. So these are two well-behaved functions that are very easy to understand. However, something really strange that might look really bizarre might not have a nice property like that. But the point is that there's some constant c and n0. So I just pick off some c and pick off some n0. Note that when I pick a different c, that will multiply every one of the values along this parabola by 2, right? It'll scale up, right? It'll stretch. That means that I would have to find a different n0. So this is just me plotting this. Now, in the technical jargon, normally after this point, normally we would say that g dominates f. Okay, so now I promised you a little bit more of a symbolic representation of big O. So let me just rewrite this with fancy notation. And then I'm going to go even a step further than that. So what I'm saying is that there exists a c. Now this backwards e represents there exists. So you notice how I wrote it out in words? So remember, this just means that there's at least one. There exists a c. Now technically you could write also an existential quantifier. That's what this thing is. You can write this backwards e again, but I'll just, for the simplicity here, I'm just going to assume that they're joined together. So there exists c and n0 such that this upside down a, it means for all n greater or equal to n0, f of n is less than or equal to c times g of n. You can go even further than this, but I think this illustrates the point that you can write this a bit more symbolically if you wanted to. I'm not going to worry too much about this, but for the sake of doing many examples, I might shorthand some of these things as we do examples. Because I'm sure as you're doing things, you'll get more familiar with what we're doing. Okay? So now I wrote this for an explicit reason. It's because when we talk about big O, oftentimes a great misunderstanding of this definition is what exactly big O is. Now, oftentimes when you say this, you'll say f is big O of g, or these are your two functions. Sometimes people say f is in big O of g, or f is order of g. I want to come back to this one right here, what this means. A common misunderstanding of big O is that it's just some magic shorthand that you can use just to simplify functions and talk about them in terms of their inputs. Now, in an algorithm sense, the input is your input size. So normally you can take reasonable considerations of the input size being like the number of items in a list when you're trying to sort the list. Or, for example, it could be literally the number of bits that you're using to measure the input. The point is that I have some input, and I want to know the order it has in relation to g. But what does this mean here? It means that I can talk about different ways of classifying functions with respect to other well-known functions. So when I write this, you believe it or not, if I give you some function like this, you'd agree with me that there are going to be many functions possibly that are also big O of g, right? So really, when you talk about big O, one thing you need to be careful of is that big O is actually a set. What do I mean by that? I mean it's some collection of functions. So another way you can write this is that big O of g of n is just simply going to be a set of functions, f of n, such that there exists c and n0, such that for all n greater or equal to n0, f of n is less than or equal to c times g of n. So believe it or not, when we talk about big O, we're actually talking about a collection of functions. So what do I mean by that? I mean, okay, so if I talk about big O of, say, n, believe it or not, there are many functions that can actually fall into big O of n. For example, n itself is a function in big O of n. You can also prove things like 2n plus 1 is big O of n. Things like 4n are big O of n. So all of these are belonging to a set. So this is actually a set. So very often you'll find that when people use the word, when they write down this relationship, very commonly they'll use at times the set theoretic in. So this means in. That's why very often you'll find that people sometimes will write big O terms in terms of sets, which is what I'll do in this bootcamp. So that's one convention. So this is the more mathematically rigorous way of viewing things. I want to give you the second usage of big O. And this one is one you'll find very often. So it's very much a convention. You'll find it's probably more common than even the set theoretic in adaptation of what big O is. So I want to talk about the other usage. Now, you may or may not have seen this one. Oh, good. I just want to make sure everybody's still kicking around. So here's another usage. Now, another way you write is using an equal sign like this. Now, I must stress that this is a second usage. It's very common in the literature and very commonly used. In fact, if you're taking a computer science class, it's very likely you're using this convention. However, I tend to use both depending on whatever is the most convenient for me. So you pick the symbol that makes the most sense for what context you're using. If you're talking about sets, you might use the set theoretic in. If you're trying to make what we're going to do happen, you might use this equal sign. Now, remember, this means is. So this equal sign is actually is. It does not mean equals. This is the most common mistake that people make, is that they assume the big O is read like an equal sign. It is not an equal sign. It is a convention that we're being used here to represent is. Now, I'm going to show you why this is very convenient. So this is a common convention. So this is a common convention that people use when talking about big O. Why would you want to use this? It's because oftentimes when we do algebra, we want to kind of overload. If you think about programming and things like that, we're going to overload the equal sign so it operates like this is. So it's going to algebraically operate kind of like an equal sign, but it's not actually an equal sign. It overrides this behavior of the big O definition. So the way you want to read this is that you read it left to right. Read it left to right to simplify. To simplify calculations. So you'll find that this notation is pretty useful when I give you things that look like this. So say, for example, I give you 6n cubed plus, say, 20n plus 8. So if I give you a function that looks like this, and suppose I gave this a function a name, like h of n. I'll do that right now. And this is h of n. So this is h right here. And I want to know what its relationship in terms of big O is. Now, I haven't yet shown you how you can simplify this down, but for somebody that is familiar with big O, you might know of some common rules, and I'll mention these here. But remember, I'm going to avoid using fluffy kind of discussions here. So you might know of some common tricks you might use. If not, don't worry. We're going to eventually get to these. Not possibly in this stream, but maybe if we do another big O bootcamp in the future. I'll show you that, well, one of the proofs I'll show you can actually generalize very nicely over that. But the point is that I can drop constants in front of terms. And also, I only have to take the dominant term. So, for example, I could rewrite this like this. So I can just drop the constants. So the way I want you to think about this is, imagine these were different subroutines that your algorithm might have, and you counted up all the operations of each step in your algorithm. So you might count these up all separately, and you would like to put them all together to get one final big O that determines the complexity of your algorithm. So you can think of this like step one. Oh, I'll read the array or something and do some other thing. This is like, oh, I do a pass through and try to figure out the maximum number. And these are just maybe your return statements or other things of that nature. So I could simplify each one of these terms using big O's like this. And I could treat it like I'm doing algebra. But be worried here, because technically, remember, these are sets. So it's only well understood underneath this convention, what I'm doing here. You can't actually technically add sets like this. This is somewhat more informal, so just be aware of that. Now, if I have a big O of n cubed, a big O of n, and a big O of 1, you'll be able to say quickly once we're done here that this is big O of n cubed. So this is the common usage for how you'd use this equal sign like convention. So this is, remember, it's supposed to read f is big O of g. So this is oftentimes how you can use this big O. So just be aware that there are some people that, like me, they'll say that this is an abusive notation. Should you not use it properly. So things like this, because remember, this is a set. So somebody might say to you, "Hey, hey Dan, this doesn't make any sense. You can't add two sets." And in fact, you probably will run into me online saying things like that. Hopefully this makes sense to everybody. So this is just an abuse of notation, but it's informal and it's very useful. So I already see that. So I can just simplify parts of my functions. I can write them in terms of big O, then I can collapse them down by removing redundant terms. Okay. Now, what does this all mean? Now, I'm going to come right back to algorithms again, just to give you an intuition of why you would want to use big O. Because you might naturally ask, well, Dan, if I'm like a computer scientist or I'm studying computer science, why don't I just count up the number of operations and do things like that, as opposed to trying to capture in terms of this weird big O thing? Like, what do those constants mean and stuff? What the heck are we doing? Well, what I'm trying to do are a few things. One, remember, we're going to be concerned with the input as it gets large. It's asymptotic behavior, which is what big O is. It is a so-called asymptotic upper bound. So I mean upper bound because if I give you a function like n, I can technically say that n is big O of n to the 100. So notice that this is an upper bound on n in asymptotic terms. There's going to be some c and n0 such that sufficiently I should be able to say this statement. But notice that this isn't really that accurate or have a notion of tightness to it. What you would actually want to probably write is that it's just n is big O of n, right? That's what I mean by asymptotic upper bound. It means as the inputs get large, there's going to exist that c and n0. And I'm going to give you intuitions of what c and n0, what exactly they could mean in a computer science context. Like, I want to be able to say something in terms of this guy right here. So one of the first intuitions you might think of is as the inputs of this function, which remember represent the operations that are done given some type of analysis, it represents the scaling of the algorithm. So as the inputs get large, which is normally how an algorithm behaves, is if the inputs get large, so if I decide I want to use your algorithm given the input where it's like 10,000 versus 100,000, I get to select what the input looks like. I might want to know how the algorithm behaves as the input gets large. So, for example, would your algorithm be good enough in practice if, say, I went from using it with n is equal to 100 versus n is equal to 10,000 or n is equal to 10 million? As it gets larger and larger, you'll notice that the behavior acts with respect to the input. That's the big point. So oftentimes people in computing will use it in terms of, they'll discuss this in terms of how well the algorithm scales. That's one interpretation of how algorithms researchers may use this, or a computer science student might use this. The way I like to use it is, I'll go back to the thing I just said before. If I give you some input where I'm counting up the instructions, I might end up with a function that looks something like this. I might end up with something that looks like this when I'm doing my analysis. What these constants are going to represent are my primitive operations. So how many CPU cycles on an actual computer, or possibly on your abstract machine for your analysis, how many steps that elementary operation will take. So the C1, C2, and C3, this, say, for example, might be how long an assignment operation takes. This might be how long a logical AND operation takes. This might be how long it takes for me to compare two numbers have a fixed size. And these are how many operations are happening with respect to each one of those simple or primitive operations. Now, you might naturally ask, okay, well, Dan, why are these constants important? It's because depending on which machine you executed your algorithm on, and remember, I'm using this in broad sense when I talk about computer. This could be a smartphone, this could be your laptop, like the one over here. It could be a big horking cluster of like something that Google has or something. It could be anything like that. It could also be a person literally executing your algorithm, pencil and paper, or asking your friend to do it. The point is that these are the number of steps that primitive operation take, which are going to be some constants. So what happens is these constants tend to interrelate with the constant c, where you can think of it in terms of a machine's speed, of how fast it could do those primitive operations. And the other point is, so c, you can think of it like almost like the speed of an operation, or these constants, if you were to add them all together. Another way you can look at this is, now if I compare two algorithms, I want some way of telling you which algorithm is better in terms of its worst case running time, for example. I want to be a pessimist. I want to know some point where one function is going to get beaten by another function, where we call dominates. It dominates another function. This is the role of n0, is at some point there's going to be some trade-off between two algorithms given any arbitrary machine that has its own constants that look like this. So you could think of it like, when I strip out these constants, it's like I'm actually stripping out the machine-dependent facets of when I think about analyzing the algorithm, given a particular machine. And n0 is supposed to be for measuring. If I give you one function and another function, I want to compare them. I want wherever that trade-off point is going to be. So you'll look at this and say, okay, well, which thing looks kind of the biggest? You'll naturally say, hey, okay, there's these constants here. You might be tempted to write something like that. This is big O of n squared. I haven't really showed you that. I haven't proven it. But the point is that these constants are irrelevant in the big O notation. So when you write it in terms of big O, what you're actually saying in an algorithmic standpoint is that you're describing any possible implementation on a computer. When I mean implementation, I mean the specific concrete description of that algorithm with respect to any computer that's going to execute your algorithm. So assuming, of course, the appropriate model of computation. Does that make sense to everybody? So this is really neat, and if you really think about it, it's kind of deep. That's the way I like to think about it, is that Big O allows you to capture all of the different machine implementations. So if I have machine 1 and machine 2, they have different constants that represent how long, say, an addition takes or a multiplication takes, and things like that under certain assumptions. So now I have some way of stripping out that machine-dependent behavior to get a special little nugget. A nugget. Think of a chicken nugget. You get a special nugget that you can use now to describe the algorithm's behavior. Okay? So that's really what I like to think about when I think about Big O. So there's kind of two ways you can look at it. There's kind of two ways you can think about it. The scaling of the algorithm, so as the input gets big, because normally when you study an algorithm, normally when it only adds like n is equal to 10, like, or some really small number, depending on the kind of problem, normally it's not very interesting to look at from an efficiency standpoint because it's very typically easy to solve. It's not always true, but it typically is. In contrast, this approach, this means that I'm giving you a mathematical way of describing the efficiency without needing to talk about machine-dependent behavior, because these constants will represent the actual CPU cycles on a machine. Okay, so that's kind of really wraps up what kind of my big points about Big O. Now I want to talk about functions. So this is really what I want to talk about now. So let's get to the meat and potatoes of this string. Let's talk about different kinds of functions, and we're going to start proving some Big O claims. So it's worth noting as I'm erasing this that oftentimes you run into this issue, like I said, that, oh, well, what if n is, I could say n is big O of n to the 100, right? Like, that is true in terms of big O. However, it's not very accurate, right? But it's technically true. There do exist other kinds of asymptotic notations. I'll talk more about those in a future stream or video. These are, if you're wanting to look a little ahead and you want to learn a little bit more about that, it's called big theta. Big theta would be the one you're looking for. So this one guarantees that there's an asymptotic lower bound and an asymptotic upper bound. The asymptotic lower bound is dictated by a so-called big omega. Now, for those that know a little bit more about calculus, you might have looked at our big O definition. You might have thought to yourself, well, that looks kind of like the definition of a limit. That is no coincidence. Some point in the future, I plan to address that. But let's talk a little bit about functions before we proceed to some examples. So I used a bunch of these big O's and I said, okay, well, what is that thing? Oftentimes, this is referred to in terms of complexity is constant. So it means that if I give you any number, that's just some constant, it's big O of 1. I'm just listing out them in terms of their order. So I can list out these big O's in terms of those sets, like I said earlier on. And I can list them out from left to right as I'm doing top to bottom here. So any function that is big O of 1 is big O of log n. And whatever's coming below it, okay? So this is big O of log n. Now, you might put log base 2, whatever base there is. It doesn't matter. I'll eventually show you this, hopefully, in a future video. This is a logarithmic function. So we would say that if it was big O of log n, I would say it's logarithmic. I'll talk more about what logarithmic or logarithms are later. Big O of n, this is linear. If I have n big O of n squared, this is quadratic. Naturally, you can keep going on like this over and over again. One that I normally doesn't get talked about enough in terms of its terminology is one that's kind of sandwiched in between these two. It's big O of n log n. Normally people just say big O of n log n. Sometimes it's called log linear. So just merge linear with log. You get it? Get it? Then I have big O of n to the c. This is referred to as polynomial. We'll talk about, believe it or not, all the main functions that fall under polynomial in this stream. So I'll be giving you actually a trick that you can use for any polynomial. So if I give you two functions that are both polynomials, I'll be able to show you that there's actually a standard trick you can use. And oftentimes in algorithms classes, I'll explain it to you, but oftentimes I don't have enough time to actually prove it. I'm going to be proving that on stream here. And you can actually see the whole technique fall out of it. That's what makes it very useful. So sometimes people ask, well, why are mathematical proofs useful? I'll explain why later. So n to the c, where this is a constant c greater or equal to 0. Then you get the ones that are not as fun to play with, are so-called exponential functions. So this is the class exponential functions. So this c here is bigger than 1, so this would be things like 2 to the n in here. Then lastly, we get a couple more. This is factorial. We're not going to talk about factorial here. And then lastly, you get things like big O of n to the n. So, believe it or not, as you work your way down, this set will consist of all the ones above it, and so on, and so on. So you should be aware of this relationship that exists with all of these big O's. So that's why I wanted to talk about the set theoretic definition, where you can contain sets of functions in other functions. So if I give you, sorry, I should be a bit clearer here. I think I misspoke. There's functions that exist in big O of 1. those functions will exist in big O of log n. But both of these sets will have functions that all of those will exist in this set, and so on, and so on, and so on. Okay? So let's proceed. So just be aware of those relationships. Now that I gave you a formal definition, I gave you a little bit of a side. I'm going to warm you up by doing a few examples. And I'm hoping that by the end of these examples, you'll get a trick that we're going to actually prove. So let's do a couple of examples. So let's get to the actual meat and potatoes of the stream, finally. There's so much stuff you have to set up to have the fun here, okay? So let's proceed. So here's the first example. So example 1, I'm going to prove that 6n squared is, let me write it out as using the set theoretic notation. So I want to prove that 6n squared is big O of n squared. Let me put this down. I don't need this anymore. Okay. So I'm going to try proving this for you, and I'll do that using the definition of big O. Now, you can either pause this video and go into the past and find that, but I'm going to recite it for you. I find very often that students or people that want to learn this stuff usually just have to play around with it a few times to really let the definition sink in. Once you get the intuition around how you might think about it in terms of algorithms, it makes a bit more sense and makes it a little easier to remember. There's just some point that you're going to be looking for. There's the game plan. So what I usually like to call the game plan is the strategy for which how you can prove the claim. So here's the game plan that we're going to have. I'm going to try to find the two constants, c and n0, such that I show that the inequality holds for all n greater or equal to the second constant, n0. Okay? So that's the strategy. So I just need to find those two constants, but oftentimes I find the strategy works best when you pick one and then you determine what the other one should look like. That's often what I do. Now, as a beginning part of this proof, I always recommend writing a little bit of what your plan is, what you're going to do. So I'm going to say we find constants c, which is a positive real, and n0, which is a positive integer. Such that for all n greater or equal to n0, now I'm going to put my functions in. Remember, this is not supposed to be like a cookie cutter. The point is that you want to think very carefully about what you're trying to argue. This opening statement is just me stating the definition within the context of my two functions. 6n squared is less than or equal to c times n squared. So that's what I've got to prove. So that's the strategy. So I'm just going to find these two constants, and if I do, such that they satisfy this inequality for all n greater or equal to n0, we're done. Okay? So that's it. So now all we have to do now is figure out a c, figure out n0 that work. So what are we going to do? Now, you could technically find n0 first if you wanted to, or you could try to find them both simultaneously by guessing and then checking. The strategy I like using, and this is the one I usually recommend to students, is you pick c first, then find n0 later. Why? Because oftentimes this stretches the function. It scales it, or rescales it, to be a bit more technical. So oftentimes you rescale it appropriately so that you can find an appropriate n0. I'm going to be giving you basically a cookbook approach that later on, where I'll give you obviously a way you can get C every single time without having to have to think about it. Very much, at least. So what should I pick at C? Let's think about it. Well, what I'm going to do, the first thing that comes to mind to me is this looks like 6n squared. Why don't I try to make it look like 6n squared? So I'm going to pick c is equal to 6. Then I'm just going to say what I need to do. Then we need to find n0 such that for all n greater or equal to n0, 6n squared is less or equal to 6n squared. Wow. Well, this should look kind of obvious too, right? What are we done basically? Can I find n0 very quickly? Yeah, I can, right? Well, for all n greater or equal to 1, both sides of the inequality (6n squared is less or equal to 6n squared) are equal right? Well, for all n is greater or equal to 1, so I'm just stating the quantity for which the statement is true. Now, I must stress, when I write a statement up here, I need to give it context. So I can't just like blindly write down something without any intention of what I'm trying to say. For example, I didn't just write this and I said, okay, is that true or false? I put it in the context of another statement. This is a big tip I'm giving to you if you're working on exercises like this or you're doing some work on this. So don't just write statements like this blindly. You quantify it. So I'm trying to tell you that I'm going to find this n0 such that this is true. Just like here, I say that they're equal, right? For n is greater or equal to 1. So what should n0 be? What should it be? It should be 1, right? Now, I'm going to choose n0 is equal to 1. Now, I must be careful here. It's not that n0 must be 1. It must be that n0 is 1, 2, 3, 4. It can be any number that is 1 or greater. So proof-wise, as long as you just give me something that works, remember, it's n0 could be any point where it's sufficient to make this inequality work, and any point after it, okay? So I could have used n0 is equal to 2 and would be fine too. But usually when you're writing up a fancy proof, you'd like to try to find the smallest n0 given some c, if you can. So I'm done, right? Not quite. I need to give a conclusion. Therefore, by choosing such constants, by the definition of big O, I can say that 6n squared is in big O of n squared. And we're done. At the end of the proof. So that's our first exercise. So hopefully you found this pretty straightforward. So the whole idea here is I find the c and I find the n0. So usually the strategy is I pick a c, then I determine n0. You might find n0 first, then pick c if you like. I prefer doing it this way, but there's many ways you can approach this. So let's do another example. Let's do another example. So let's do a second example. By the way, if you're in the chat and you want to ask any questions, just feel free to ask. So if something wasn't clear to you, just let me know. So let's prove another example here. Okay, so what we're going to do is we're going to prove n squared plus n is big O of n squared. Let's make it more interesting. Let's put it as 12n. So n squared plus 12n is big O of n squared. We're going to prove this. So let's write out a proof. What's the first thing I do? I usually write out the game plan, what I want to do. So we need to find constants C, which is a positive real number, and n0. Now, I should stress that I'm oftentimes using this set theoretic notation to denote what C and n0 are. If really you don't like that, just simply write out the words. Just say, we need to find constants, find a positive real constant, C, and a positive integer constant, n0. Maybe in the future example, maybe I'll do that. We need to find constants, C and n0, such that, now I'm going to write it slightly differently, but remember, I'm just saying the exact same thing, such that n squared plus 12n is less than or equal to c times n squared for all n greater or equal to n0. So I just need to find c, and I need to find n0. The real question is, what should I pick at c? Let's figure out an appropriate c. Seems like there's a staple on the thing. What should I pick as c? Well, I'm going to use a similar kind of trick. Now, I want you to think about this in a somewhat different way. Imagine if I pretended that 12n was actually 12n squared. I want to use that same trick I used last time, where I try to make whatever's on this side look kind of like this one here. So what am I going to do? I'm going to pretend that 12n is actually 12n squared. Do you see what c should be now? Well, if it's n squared plus 12n squared, that would be 13n squared, right? So what should I pick at c? I'm going to pick c to be, naturally, let's pick c is equal to 13. Now, this is a little bit of a style thing that you should be aware of, is oftentimes when you make arguments, you want to kind of, you normally come up with some idea on the top, off the top, maybe right off the side, then you want to splice it together in the correct way such that you're not making a false statement. So, when something is clear enough for the reader, oftentimes I'll phrase it in terms of observing something or noticing something, or to remark about something. So I'm going to be pointing out something so that I can follow my chain of reasoning here. Because I would like to figure out what n0 is without doing much work. Because I don't want to make this a lot more complicated than it has to be. I'm going to say, notice that for all n greater or equal to 1, I'm just going to put in what my idea was, right? I'm just going to go n squared plus n is going to be, is it n or is it n? It's 12n, right? 12n. This is less than or equal to n squared plus 12n squared, which is equal to 13n squared. As, now I have to give my reason why this holds for all n greater or equal to 1. I can't just state this without a reason. You might say, oh, Dan, that's kind of obvious. When you're doing a rigorous proof, you have to give some justification. depending on your audience, of course. I'm assuming an undergraduate computer science background here, so I usually like to make sure I put justifications down. For an expert, this would be obvious. In fact, an expert might literally eliminate this entire step right here. As n squared is less than or equal to n squared for all n greater or equal to 1. This statement is quite obviously true. That's literally what we used last time. Now, I don't like to use the word obviously, but these two sides are literally equal to one another, right? At least algebraically. So this should hold for all n is greater or equal to 1, right? That's literally what we did last time. You'll notice that my examples are going to sort of stack on each other. And 12n is less than or equal to 12n squared for all n greater or equal to 1. That's my justification. So I take each part of my inequality. So I have n squared, I compare it against n squared. I take 12n, I compare it against 12n squared. Obviously, if I add those two together, the left-hand side together, and the right-hand side together, I can state the whole statement on each side. Okay? So I'm just taking n squared plus 12n. This is the left-hand side. I know that each of these, when I compare each term separately, that it is, in fact, true. So when I add these sides together, it should be true as well, right? When I combine them. So I'm just combining these two inequalities to get that chain of reasoning there. And I'm just picking off n. There's our n squared equal to 1. Now you might naturally ask, where the heck did, how do you know this? Well, just divide by 12 on both sides of this algebraically, then divide by n. So if you just divide by 12n on both sides. This isn't part of the proof, I'm just justifying it for you. This just becomes 1. And the power 2 goes away, and then this just becomes n, right? So then n is greater, so n is 1 is less than or equal to n, which means that n is greater or equal to 1. Okay? So there's our justification. So I'm just going to choose n0 is equal to 1. Therefore, by the definition, I'm going to abbreviate definition here. Definition of big O, n squared plus 12n is big O of n squared. That's the end of the proof. We're done. So does everybody see the structure here? I have my introduction, where I describe what I'm going to do. This is very basically just the game plan. I'm describing what I'm going to do. And then I pick C, then I do some step that justifies my selection of n0. And then I do a conclusion just remarking what I'm going to invoke. I just invoke the definition of big O. That's all I did. Okay? So that's that. Now, I want to do a little bit of an aside here. I want to ask you some other question here. You notice I picked the C and an N0. I want you to think a little bit about this. I'll just do one example of this with you. I want to know which C's and N0s work. Sometimes there only exist certain C's and certain N0s for some examples. Other times there just exists an infinite number of C's and N0s you can select. So I'm going to take this example and I'm just going to break it down a little bit for you. So now, remember, I just told you that you'd write words to attach to the inequalities. I'm just doing some scratch work with you so that you can see how C and N0 operate with respect to these two functions. So I'm just going to do an algebraic manipulation. I'm just going to move the 12n onto the other side. No, I'll move n squared. Let's move n squared. So I have 12n is less than or equal to cn squared minus n squared, which I'm going to simplify a little further. Let's rewrite this. 12n is less than or equal to c minus 1 times n squared. So I'm just going to factor out the c. So I'm going to take n squared and I'm going to factor this with respect to c, okay? So now I have, if you notice, I can expand this up with n squared, so I get cn squared, and I have n squared times -1, right? Which is right there. Okay. So I'm just going to divide both sides by n. So we still have a term on the right-hand side. So I end up with 12 is less than or equal to c minus 1 times n. Can you use c is equal to 1? Can we use c is equal to 1? No, right? If you put 1 in here, this is going to become 12 is less than or equal to 0 times n, which is never going to be true. So c is not equal to 1, which makes natural sense, right? Because n squared plus 12n is strictly bigger than n squared, right? But what can we do here? Well, let's think about c is equal to 2. Now remember, c is a positive real constant. It doesn't have to be just like the numbers I'm picking. I'm just giving you a general pattern. So if I pick c is equal to 2, well, n, you'll notice that I can do a little bit more rearranging. I'm going to divide both sides by c minus 1, which should be valid to do if c is in fact greater than 1. So I have 12 over c minus 1 is less than or equal to n. So all I'm going to do is I'm going to plug in what c is each time, and we're going to see if there's any pattern that arises. So 12 over 2 minus 1. So 2 minus 1 is just 1, right? So you would pick n0 to be equal to 12, right? So if c is 2, then n0 would be 12. How about when c is equal to 3? Well, that would mean that n is greater or equal to 12 over 3 minus 1, which this is equal to what? Is equal to 6, right? 12 over 2, right? That's 6. So just make n0 equal to 6. You can keep doing this. Suppose you consider 6. So n is greater or equal to 12 over 6 minus 1. Now this is 12 over what? 5. But what's 12 over 5? It's not an integer, right? So I need to do something to it such that it works, right? So I'm going to let n0 be whatever is the result of this, and I'm going to round it up. I believe it's 2.4 or something like that. I'm going to round it up. I'm going to use a so-called ceiling. So this is the ceiling of 2.4. So ceiling just means round up. So if I give you x with the ceiling, so these two upside down L's that are mirrored, this just simply means that I'm going to take x and I'm going to round up the next integer. So if, for example, I give you 5 and 5 is in the ceiling, you just put me 5, right? But if it's 5.5, the ceiling of 5.5 is 6. So notice that now, if you notice this, if I make sure that n0 is always an integer, you see what you could always pick as c and n0. Well, c could be any constant greater than 1, where n0 is greater or equal to the ceiling of 12 over c minus 1. I'm not going to prove that for you, but I just want to give you the intuition. So I just use this algebra over here to figure out a general pattern for this example. So if, say, for example, somebody asked you, hey, look, which C's and N zeros work? If you do a little bit of algebra, you can try to get it so that you have C in terms of N, and then you can perform the arrangement so that you get the inequality looking something like this. Then you can determine what N0 might look like. So this is just an aside. This is not a proof. This is just me describing to you how you can find a general pattern of what a C and N0 might look like. So these would be a set of all valid pairs of C's and N0s. So that's second example. So like I said, when you pick a C, it might change what N0 is. Or at least a valid N0. I should be a bit more precise, a valid N0. Okay, let's do another example, and I'm hoping this will hammer in the trick that I've been using. Let me get my next example. Okay. Let's get something a little bit more complicated. So at first, this is going to look a little bit more daunting if you're not familiar with polynomials that look like this. I'll define what a polynomial is, at least in our context, in a moment. So I want to prove that 4n to the 4 plus 3n cubed plus 2n squared plus n is big O n to the 4. Or n to the power of 4. This looks really complicated, but believe it or not, we actually have the recipe. What am I going to do? Before I write anything down, I want you to think and look at this function for a bit. What if I were to pretend that this cubic term is actually n to the 4? I pretend that's n to the 4 and that's n to the 4, and I can use the same trick I did before, right? Well, while I write down the first sentence, I want you to think about an appropriate C for our constant. So we need to find a positive real constant C. See, I said I was going to write out words for you. And a positive integer constant N0 such that for all n greater or equal to N0, I gotta write the whole thing, 4n to the 4 plus 3n cubed plus 2n squared plus n is less than or equal to C times n to the 4. Okay, do you have your constant C for me? Well, look, let's see. 4, 3, 2, and 1 maybe? The 1 right there, because it's just a 1. Maybe I should just add those up, right? What should C be? I'm going to pick C is equal to 10. Now, I must mention that some people like to just describe what C and N0 are at the end of their proofs. I prefer doing it as you're arguing. So just keep in mind when you're doing these kind of exercises, the kind of style that typically your professor, or say if you're doing a course, look at their style they do it in. However, you'll find that I'm being somewhat more rigorous here. So some people will be happy to overlook certain statements. I won't be. Why? Because I want to hold you accountable, just like you'd want to hold me accountable when it comes to saying things that are true. That's at least how I think things. It's like a two-way street. Just like I don't think I'm better than you, right? You and I are friends. Okay. So if I cheat, you have to let me know. Okay, so let's see here. So I'm going to pick c is equal to 10. Then, like I said, we need to find n0 such that that over there is kind of melting in the microwave. Such that for all n greater or equal to n0, 4n to the 4 plus 3n cubed plus 2n squared plus n is less or equal to 10 times n to the 4. Well, now I'm going to make the same kind of observation I did last time. Here we go. Well, observe that. We'll observe that 4n to the 4 plus 3n cubed 2n squared plus n is less than or equal to 4n to the 4 plus 3n to the 4 plus 2n to the 4 plus n to the 4, which is equal to 10n to the 4. As, now remember I got to give my justification. As, now I just going to use the same trick, right? I look at each one of these pieces, and I consider them all separately, and then I add all of the ones on the left-hand side, and I add all the ones on the right-hand side, and then I can say the statement is true for all of them. Oh, I think I forgot to say for all. So I have for all n greater or equal to 1 right here. As 4n to the 4. I was just about to write 4n squared. 4n to the 4 is less than or equal to 4n to the 4. For all n greater or equal to 1. 3n cubed is less than or equal to 3n to the 4. For all n greater or equal to 1. Does everybody see how you do that? You just divide both sides by 3n cubed. You end up with a term on this side where it says n is greater or equal to 1. Okay, 2n squared is less than or equal to 2n to the 4 for all n greater or equal to 1. Same idea. Divide both sides by 2n squared, and you would end up with n squared as greater or equal to 1, which naturally should imply that n is greater or equal to 1 in the context of where we're talking about here. Okay, so lastly, I need one last one here. N is less than or equal to... You can see how this gets very, very redundant after a while. But you should still try to do the work. So there's my justification. Now, this isn't the only way you can argue this. But I find this is the easiest way without having to throw out any extra tools. I just take each one of the pieces, I add all the ones on the left-hand side, I add all the ones on the right-hand side. And then I could chain them all together over the largest number that fits all these. So now I just need to finish this up. So what am I going to say? I'm going to choose n0 is equal to what? Can I pick 2? Yes, I could pick 2, but I'm going to pick 1. Then, what are we going to do? We give a conclusion. So I'm going to leave it to you to try writing out a conclusion for this example, because I'm running out of space on the board here. So let's proceed. Now, do you see a kind of trick that I'm using? How am I picking C every single time? Am I really just trying to find something that looks similar to it? Or am I just really just doing something that's actually far more systematized? I'm actually doing something far more systematized. And this is actually going to derive the trick that I told you about earlier on where you can drop things like constants. But it also is the same rule that also dictates that you can also use the same rule to also dictate that you always pick the dominant term of a polynomial. So for example, you notice that I didn't really care too much about those cubic and the square term and all that. That wasn't really relevant. It was really the n to the 4. Do you see how that proof would break down if I were to say that was big O of n cubed? Well, the one part where I justified 4n to the 4 was less or equal to 4n to the 4, and now it would be 4n to the cube, which would fall apart for that proof. Now, I'm not going to worry about proving when it is not that. That is not the point of this boot camp. I might do one like that in the future. If you like that, let me know in the comments. Now, this brings me up to talking about kind of like the first really big trick that I want to show you. It involves polynomials. So, what's a polynomial? So they have the form, they look like this. So I'm going to call it P of n. And each one of these terms is going to have a coefficient. So this is going to be a constant. So a0, that is a constant, raised to some power k, where k is a constant, plus a1 times n to the k minus 1, plus a2 times n to the k minus 2, and it goes all the way down to a k minus 1, n to the power 1, plus a k n to the power 0. It's worth noting that n to the power 0, this is just 1, right? Now, if you're like me and you don't want to write this out every single time, you can use summation notation to rewrite this like this. So if you're not familiar with this notation, all it really is saying is I'm going to add whatever's in here. I'm going to do it over from I is equal to 0. This is the lower limit of the summation up to the upper limit of the summation. So notice that this starts at 0. It goes 1, 2, all the way up to k. So I'm adding over all of these terms. So this is typically the form I'm going to be talking about when I talk about a polynomial. So I'm going to say where coefficients. So these are those terms, the a terms there, where coefficients, a0, a1, all the way up to ak. These are all going to be non-negative real numbers. So remember, this is just saying that it cannot be a negative number. Actually, I'm going to make this more interesting. Instead of making it just non-negative, I'll just leave it like this. I'll assume that they're non-negative. So they can be 0 or some positive term. However, what I'm going to write here can generalize quite easily to when it has negative terms. You're just going to do something slightly different from what I'm going to show you. Basically, you're just going to discard the negative terms. So, believe it or not, that trick I've been using can actually be viewed in a somewhat different way. And it actually exactly has to do with these coefficients. Did everybody see that? When I gave you an example before, what was the example I gave you before? It looked like this, right? It looked like this. 4n to the 4, and I had 3n cubed, 2n squared, n. Now I want you to imagine each one of these terms. And imagine these have a toggle switch on them. Now, I'm going to include another switch over here. It's going to represent the power that I didn't include that looks like our polynomial here. So notice that I have 4, 3, 2, 1, and 0. Now, to make things a little simpler, we'll have each one of our coefficients here. That's 1, and that's 1. Now, I want you to imagine these like switches. Now, this was not a part of my polynomial. So I've just rewritten it in terms of that form there. So I'm going to turn it off. And the way I like to view this is, imagine you're trying to turn on a light. If the light gets turned on, please forgive my lights. So if the light is turned on by the switch, you're going to add the coefficient to your C. Do you see how now I got that constant? You see the trick? I write my polynomial on my first function in terms of all of the coefficients. So I have all my coefficients and I write them out in this form. Like I said, if you have negative terms in here, that's fine. Just discard them. So in the analogy I'm describing here, whenever you have a negative term, just turn it off by default. That's all I'm saying. So if the coefficient is 0 or less, you can just turn it off, right? So do you see how I got my constant from my previous example now? So my proof is going to lay out this idea without thinking about cute light bulbs and switches. But believe it or not, this idea is good enough for dealing with any two polynomial functions. So let me lay out the claim. So remember, this is the polynomial I'm going to be concerned with. This is what the coefficients look like. However, like I said, it's very easy to modify what I'm going to do. If you wanted to talk about more general polynomials. At least if you're interested in tricks. So here's the theorem. So this is the theorem we're going to be concerned with. So theorem. So this is the statement of truth that we're going to prove within the context that I've defined. So I'm going to say given constant k greater or equal to 0, and the given coefficient then you can say the following. P of n, remember P of n, that's the name of the function I'm giving. You can just say P if you wanted to, but I'm going to use it in this somewhat of abusive notation as a shorthand. P is big O of n to the k. So we're going to prove this. And how we're going to do it? Believe it or not, the proof is very simple. But you're going to find that everything we've been doing this entire time turns into this argument. So what is the first thing I do? I lay out what I'm going to do. I'm going to say that we find constants. C and n0 such that for all n greater or equal to n0, P of n is less than or equal to C times n to the k. We're going to use the exact same trick I just told you. you're going to pick C such that you add all the coefficients of the polynomial. So I'm going to take all those coefficients, I'm going to add them all together, which you can rewrite that over there as a sum with lower limit 0 and upper limit k. That looks like this. Like I said, this proof is not very hard to modify to allow for more general polynomial with negative coefficients. Which once you have negative coefficients, you can include subtracted terms and so on. It all really rests on changing what this is. Does everybody see that? So that being said, we can proceed. Now, actually, I should be a bit more precise. I'll let you think about if that C still works. But I'm not going to prove that claim here. However, I have a feeling you probably should be able to have no problems. See, a part of me is just trying to be very careful, which is what I want to do here. Because obviously I'm live right now when I'm doing this. It's been a little while since I've thought about that case. But I imagine you probably could still make this work. Actually, I'll give you a tip. Put absolute value signs over those coefficients. That should easily fix anything you have to deal with. So, I did the work for you. So, if you want to deal with negative coefficients, just literally put an absolute value over this so it gets rid of the negative signs. That should definitely bound properly. So, anyways, we have this right here. Now, what am I going to do? I have my C. What's the next thing I do? Well, I then try to find n0, right? Then observe that for all n greater or equal to 1, P of n is equal to the sum of each one of my AI n to the power of k minus I terms. Right? That's what it equals. But this is in fact less than or equal to the sum from I is equal to 0 to k of AI. Now, before I write down what I'm going to write down here, look at this. Okay. Would you agree with me if I subtracted off anything other than 0? Like if this was 1 or 2 or 3, this term would actually get smaller, right? So all I'm going to do is I'm just going to literally just write n to the k here. Which I can rewrite because, look at this. This is a product. This is multiplying these two numbers here. But remember, n to the k doesn't depend on this at all. So I can factor out n to the k from this summation. That is a property of summations, like this. Does everybody see that? So I'm going to justify this step right here as AI times n to the n to the k minus I is less than or equal to AI n to the k, which we're going to use the same strategy I used before. I divide both sides of this inequality by the larger power, which would be what? It would be, well, sorry, the smaller power. It would be k minus I, divide that on both sides, and I end up with something on this. So I'm just going to rearrange here. I'm going to just divide both sides by AI n to the k minus I. And I should end up with 1 is less than or equal to n to the I. I'll let you check that. for all 0 is less than or equal to I, less than or equal to k, and n is greater or equal to 1. So what should I pick as n0? What should I pick? I pick n0 is equal to 1. That's the exact same one I've been doing every single time, right? Choose n0 is equal to 1. Now, I must stress, n0 isn't always 1, as we're going to see later. But you'll find that if you use this strategy, it's very easy to get n0 to be 1 if you wanted to. Remember, n0 can be 2 in this proof. That's perfectly fine. It could be 3, it could be 4, it could be 10,000. But it's not very reasonable when you go that big. You want to find something that's rather insightful. Choose n0 is equal to 1. Therefore, by the definition of big O, P is big O of n to the k. And we're done. By the way, you've been noticing I've been drawing boxes. That one's kind of melted in the microwave. But this is to signify the end of a proof. So, believe it or not, this proof is very simple, and it actually gives you the recipe to deal with all the cases we've seen before. Like I said, if you want to generalize this so that the coefficients are allowed to be negative, just simply put an absolute value sign along on the coefficients. So you pick C, and that should allow you to make this inequality work. And you would just appropriately use absolute value signs. It takes some small tweaks, but the point is that it's easy to generalize this theorem even further if you like. I just picked this one because it's pretty intuitive. Here's somebody's phone ringing. Anyways, we're going to do one final example because we've seen plenty of examples at this point. But I really like to leave you on something a little bit less formulaic like this. I want to do something that will actually just be like, that's kind of neat. So we're going to do that. So this is going to be the final example, but I'm going to require a little bit of primer on logarithms to describe it for you. So let's talk a little bit about logarithms. Hopefully you're having a good time here. I'm having a good time. I'm hoping to do more of these streams. I can do more examples like this or do other topics. So just do keep in mind that I put a lot of time and work into these videos and streams. So I'm hoping that you'll support in what I'm doing here. It's a lot of work. Okay, before we get to our final example, I want to ask you a very basic question. Well, it's actually not that basic, but I want to ease you into thinking this is easy, which I think once you really get it, it's not too tough. So given some positive real number, x, and b greater than 1, which I'll just assume is some positive real. But typically we use it as an integer or a rational. So what power y is so that b to the power y is equal to x. So if I give you b and I have x, I want to know what should the exponent be such that if I raise b to y to get x, I want to know what y is. So for simplicity, I'm going to assume powers of 2. So I'm just assuming implicitly that b is equal to 2 here. So let me write out some powers of 2. So you might know some of these. So I'm going to do 1, 2, 4, 8, 16. And if I wanted to get some general term, it would be like 2 to the power of n, where n is just some positive integer, right? Or it could technically be 0 as well, because 2 to the power of 0 is 1. So let me write down all the powers. This is 2 to the power of 0. This is 2 to the power of 1. This is 2 squared. This is 2 cubed. This is 2 raised to the power of 4. And this is just 2 to the power n, right? So these are just powers of 2. I want to figure out what y would be. So what's y going to be? Y is equal to, in this case, 0, because it's 2 to the 0 that equals 1. 2 to the 1 equals 2. 2 squared, or 2, equals 4. 2 cubed equals 8. And 2 to the power of 4 is 16, so y would be 4 here. What would it be for 2 to the power of n? Well, it'll just be n, right? Is that neat? So that's just n, which is a neat property of logarithms, by the way, but I haven't defined what a logarithm is yet. So a function describes, a function that describes y in this way is called a logarithm. So we're just playing a little game. I just want to know what the exponent is. So abbreviation is log. So if you're looking at this from, if you're familiar with exponents, logarithms are the inverse of exponentiation. So notice that if I wanted to know the result of 2 to the power of 0, I get 1. Instead, I'm asking the question of, if I have 1, what power does 2 need to be such that I get back 1, right? So I'm asking a somewhat reverse question, right? So I give you a number. I want to know what the exponent is such that I get that same result, right? So the answer I'm looking for the logarithm is always the exponent. Okay, so that brings me to defining what a logarithm is. Once we have that, we can actually talk about the final example, which should be a good time. So here's the definition of a logarithm for our purposes. So if b to the y is equal to x, or b is greater than 1, and x greater than 0, as defined above, I'm just going to finish writing it up here. Then log, which I'm abbreviating as logarithm. So I'm just going to say log instead of logarithm every single time, depending on what I need to say. Then logarithm base b of x, which is denoted as log base b of x is equal to y. So do you see how these two are related? So I have an exponentiation occurring over there. What y is the result of b and x being known to find out what y is. So let me do some examples just to illustrate this. So 2 quick examples, and then I'll erase the rest of the board here. Okay. What's log base 2 of 8? What's log base 2 of 8? So remember, you got to think about it like this instead. Log base 2 of 2 cubed Do you see what the answer of log base 2 of 8 is now? Because I just rewrote 8 in terms of powers of 2, right? I just did all the work for you. So what is it? It's 3, right? As we established over here. 8 is 2 cubed, which y will be 3. How about just to illustrate this point, and this is, by the way, the reason why I defined the complexity function the way I did, at least for this session. Okay, what is log base 2 of 1? What is it? Okay, so what power do I need to raise to get 1? 0, right? So there we go. So believe it or not, that's all we really need to know to get our setup for what we're going to do next, which is going to be a little bit more complicated than the other examples we've done. So you're going to find this to be, if you're looking for something that's going to be a bit more challenging, this is the one to look for. So now that we know what a logarithm is, and we've seen a couple examples, I should hopefully convince you that that what we're going to look at next might be interesting in its own right. Okay, just seeing how everybody's doing here. Not seeing any comments. I think we're good to go. Okay, so what we're going to consider next is a so-called finite harmonic series. So I'm going to define what is called a harmonic number. So a harmonic number. So given some integer n greater or equal to 1, the nth harmonic number is as follows. I'm going to write it in terms of a function. However, very often when you talk about this mathematically, often people will write it like this. Hn, like this, with a subscript n. I'm writing it explicitly as a function to make it a little easier to see that we're talking about a function. Because that's what we're going to look at it as. It's a finite series. Okay. There we go. So I'm going to define it here for you. So it's going to be the summation from I equal to 1 to n of 1 over I, which is written as 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, all the way up to 1 over n. So now I'm going to write down what we're going to prove. So this looks somewhat daunting in its own right because we're adding a bunch of terms together. And they tend to get smaller and smaller and smaller. But it's not really quite clear how this behaves, at least to somebody that's never seen a harmonic series before. So here's the final example we're going to do today. So for the final example, we're going to prove that Hn is big O of log base 2 of n. So I'm actually going to prove that this is in fact on the same order. Sorry, it is of the order of a logarithmic function. At first, this looks a little daunting, so I'm going to do some setup. What's the first thing I always do? I say what I'm going to do. I'm going to give my game plan, right? Let me get my hat. I think get the hat on. I think that makes things more fun. Ah. It can't be big old boot camp without the hat, okay? So we need to find C, which is a positive real number, and N0, which is a positive integer, right? So that for all n greater or equal to n0, h of n is less than or equal to c times log base 2 of n. Now, what I'm going to do next is the big trick that's going to make things a lot easier for us. So just follow this very carefully. Otherwise, I would have to make more assumptions. How noises up here. Before we do this, let n be rounded up to the next power of 2. So that I'm going to define m. M is equal to 2 to the power of the ceiling of log base 2 of n. Remember the ceiling? It means I give whatever's in between here, I round up the result of that to the next nearest integer. So what do I mean by this? For example, if I knew that I had, say, n was equal to 5. Say n is equal to 5. What I'm saying is that log base 2 of 5, which I believe is like 2.32 or something like that. This is, I imagine it's probably equal to it, but no, it's approximately equal to it, I think. 2.32. You can tell me in the comment section. So this isn't going to be sufficient for being a proper power of 2, so I'm going to round up this so that it's 3. So for example, if I give you 5, the next power of 2 would be what? Well, it's bigger than 4, so it's going to be 8. So if I give you 5, next m is going to be equal to what? It's going to be equal to 8. If it was 9, it would be equal to 16. If it was, say, 3, it would be equal to 4. If it was 4, it would just be 4, because it is a power of 2. So, let's proceed. Now, I want you to observe something really important. It's we potentially, either we got a power of 2 on our hands, or we round up the number to the next power of 2, which means m is what in relation to n? What is it? I'm going to say it here. Note that n is less than or equal to m. Then I'm going to define a useful variable for us. Then let k equal the ceiling of log base 2 of n. You'll see why I do this. It makes things a lot easier to do for my calculations rather than playing with m all the time. And I'm going to do the following. I'm going to do a little trick here. So I'm going to relate the nth harmonic number with this m here. Because remember, we've established that n is less than or equal to m, right? But that also means something interesting. If I am applying the logarithm, if I give you a number that's smaller than another number in the logarithm, what does that actually look like when I actually raise it to another power? Well, 2 to the logarithm of that number, when I round it up, should be in fact bigger or equal to the original when I do this operation. So I end up with this. So h of n, which is equal to the sum of 1 over I. So I'm just going to write down the definition of the nth harmonic number. So I sum from I is equal to 1 to n. Now here's the trick I'm going to use to get rid of this issue. This is going to be less than or equal to the sum from I is equal to 1 to m. Now remember, m is bigger than or equal to n. meaning that this has to be true, because if you look at their definition, that means I'm going to have possibly more terms over here I'm adding. So this should not be very difficult to see, this step right here, because all I'm doing is adding more terms. So it's either going to be equal to it, or I'm going to add possibly one or two, or possibly some other set of terms. So now I have this. So I'm just going to write down that, but I'm going to write it in terms of k. 1 plus 1/2 plus 1 over 3 plus 1 over 4 plus all the way up to 1 over, now I could write 1 over m, but what's m really? It's that, but remember, what's k? This. So it's 2 to the k. But what's this? What's this right here? What harmonic number is this right here? This is what? This is h of 2 to the power of k. So now we can play around with this, and now we have a sufficient upper bound on the nth harmonic number. So let's proceed. Okay. So now here's the trick. I'm going to play around with h of 2 to the power of k. And because of the number of terms it has, I can actually group them in a special way, so that I end up with something I can actually group by terms and construct a second series that I can compare against it. I'm going to say then we can formulate a second series. I'm just going to make another series. We had one series before. Here's my second series. As follows. Now, I'm going to write the second series in a somewhat strange way at first, but you'll see that I'm really just using the exact same trick I used every single time before I figured out my trick with the polynomials. So I'm going to use that same trick, where I'm going to write down the first series on one side. I'm going to write this new series I'm going to construct on the right side. And then we're just going to add those terms together so I get a valid inequality. So here's the big trick. So I'm going to write down the terms that I had before. But I'm going to do it in terms of the number of terms that series actually has, which is all actually being expanded out by powers of 2 if you actually think about it. I'll let you think about it, but it should hopefully be evident from this. We have 1/2 plus 1 over 3, right? 1 over 4 or 1 over 5 plus 1 over 6 plus 1 over 7. So I'm going to keep writing out the terms like this. Eventually I'm going to get to 1 over 2 to the power of k, right? But I'm going to keep writing them down. 1 over 2 to the power of k minus 1 plus 1 over 2 to the power of k minus 1 plus 1. And this should be the one just before 2 to the power of k in the denominator, right? So these are all terms in the left-hand side series, right? And then we have the final term right here. So you'd agree with me that everything on the left-hand side is actually the series that I wrote out just before. Now what I'm going to do is I'm going to show you a neat trick that very often people use in analysis to deal with harmonic series. It's a nice trick. So notice that by grouping the terms like this, you notice that the number of terms actually relates to some power of 2. I'll come back to that in a moment. So notice there's one term, 2, 4, and then actually 8 here, and then we just end up with this weird one term down here. So what can I say about this? What I'm going to do is each one of these groupings, I'm going to simply write each term in terms of the power of 2 in the denominator on the first term. So does everybody see that? That every single one of these first terms is going to end up being a power of 2, right? In the denominator. So I'm just going to write that out. I can do the same thing here too. I just write 1 over 2 to the power of k minus 1, right? Keep doing this. Now, because I haven't really wrote a finite number here, this is happening 2 to the power of k minus 1 times. My tablet is dying. It can't handle this analysis. So did everybody see that this is in fact all of these groupings? So this group compared against that, this, each one of these, when I compare it against these terms, this should be satisfied because notice that 1 over 5 has to be less than 1 over 4. 1 over 6 is less than 1 over 4. 1 over 7 is less than 1 over 4. Same is true in each one of these, except for this bottom one. The bottom one is just going to be written exactly the same as I had before. So this is just simply what I had before. This is the new series that I'm constructing. So this is constructed by writing out the powers of 2, the number of times this number appears. So I write this out twice. I write this out 4 times. I write this 2 to the power of k minus 1 times. Then I append the final term of the original series that I have. So what am I going to do now? Now this is where all of this lovely trickery will actually come into play. So the second series is the one I wrote on the right. If you're careful, you could write it out as a double summation. I'm not going to do that here. So I've written out the second series. Now I'm going to use this in a very interesting way. So h of n, so the nth harmonic number is less than or equal to h of 2 to the power of k, right? So the 2 to the power of k harmonic number. This is less than or equal to my second series now. 1 plus 1/2 plus 1/2 plus 1/4 plus 1/4 quarter plus 1/4 plus, and this goes all the way up to 1 over 2 to the power of k minus 1 plus 1 over 2 to the power of k minus 1, and so on. So there's a group of those here, 1 over 2 to the power of k minus 1 plus 1 over 2 to the power of k, that final term. Okay. I want you to look very carefully at this. So this series that I've constructed is very special. Do you see why? I want you to look at it in terms of the groupings that I did of the terms. So I clustered those groups in chunks. How many of these exist? Remember, I told you that I write 1/2 2 times. I write 1/4 4 times. I write 1 over 2 to the power of k minus 1. I write that 2 to the power of k minus 1 times, right? So when I add up these terms, how much does that sum to? Well, it's 2 times 1/2, which is just 1. This is 4 times 1/4, which is just 1. This is 2 to the power of k minus 1 times 1 over 2 to the power of k minus 1, which is just 1. But that means I have actually a whole bunch of 1s that I'm adding, plus this final term. But what is that? Well, how many of these do I have? So this is what happens when I have 2 to the power of 0, right? Then I have 1, then I have 2, then I have 3, then I have 4. I do this up to k minus 1, right? Well, from 1 to k minus 1 is just k minus 1. But I have this initial first term here, which means that it's going to be k ones that occur. That means it's going to be k, because it's k times 1, because there's k ones being added, plus the final term. Isn't that neat? So now actually I have an actual nice formula here. So recall, so I'm just going to remind you of some notation we've used. Recall that k is equal to the ceiling of log base 2 of n, and n is less than or equal to m, which is in fact equal to the power of k. So now this is where the chaining of reasonings can all come together. Observe that for all n greater or equal to 1, h of n, or the nth harmonic number, is less than or equal to k plus 2 to the power of k. Remember, that's because of this inequality up here. Remember, it started over here, and it's less than or equal to whatever came out here. Which this, well, what's k? K was the ceiling of log base 2 of n. Well, what's 2 to the power of k? That's m. 1 over m. Now, if I take some number and I round it up, would you agree with me that if I added 1 to the result inside here, it should bound from above or match the ceiling? So, for example, if I have something like 1.1, when I use the ceiling on 1.1, I get 2, right? So if I add 1 to 1.1, I get 2.1, which is bigger than 2, right? So it's either going to be equal to it or possibly bigger. So I'm just going to use that little trick here to get rid of the ceiling. So now the ceiling log base 2 of n is less than or equal to this. Remember, I'm doing this all over that n is greater or equal to 1 here. Now, because m is greater than or equal to n, I can replace m with n in this inequality because it'll be bigger, right? Because n could either be equal to m, or there's a possibility that we can have it where these two are going to, in fact, this is going to be smaller, right? So what happens? Well, I can write this again. So you would agree with me that for any n greater or equal to 1, that 1 over n must be less than or equal to 1, right? So I can just simply rewrite this again. Of log base 2 of n, log base 2 of n plus 1 plus 1, right? Which this is naturally equal to log base 2 of n plus 2. Now you notice that I haven't really done a whole lot of picking c and n0. It's because I've been doing a lot of setup, so I have a connection between the nth harmonic number and the logarithmic function. Did everybody see that? So now I have a direct connection between these two. So I did some setup, but notice the way I set up my proof, I didn't just simply insert this randomly. I eased it in by premising for the reader that I was going to do some derivation. Everybody see that? Kind of slick, isn't it? So now, because I have this, you just want to avoid doing this too much. If there's a lot of work here that it seems completely out of place, maybe put it aside and prove it separately. Because when you prove it separately, you can just invoke it later. So now, I want you to think about this. Now I have the nth harmonic number, and I have log base 2 of n plus 2 at our disposal. Now what I would like to do is make something that looks like this, look like a logarithm. I would like to get rid of this 2 somehow. Now, this all really comes down to how you pick c and n0. Now I have two terms here. I have a logarithm term and I have that 2 right there. So I'm going to use c is equal to 2 to match the number of terms. And I'm going to make n0 big enough such that the logarithmic function that I have in place for 2 will be bigger than 2 or match it. So that's going to be the strategy that I'm going to use. So I'm going to use c and n0 together to get an appropriate pairing. Pick c is equal to 2. And then we need to find what? Find n0, right? So that h of n, or the nth harmonic number, is less than or equal to 2 times log base 2 of n. So now we're going to use everything we have here and combine it with this here. So I'm going to come up with that on the right-hand side by using appropriate n0 for my algebra. This is what makes this example kind of slick. So notice that when n is greater or equal to 4, h of n is less than or equal to log base 2 of n plus 2, right? That's what we have right here, which is less than or equal to log base 2 of n plus log base 2 of n. Why? Why is this? When n is greater or equal to 4, what can n possibly be when I put it into log base 2 of n like this, if it's 4 and greater? What's log base 2 of 4? It's 2, right? So that's basically my game plan here. I wanted to make something that looks like a 2. So notice that this is going to be greater than or equal to 2. Remember, because of the argument I made earlier about how the logarithm behaves, this is in fact going to be a true statement. The logarithm doesn't do this. It simply will, it doesn't go back down in terms of its value. It goes up. That's, if you want to get a bit more rigorous with that, you pull out some calculus if you like, but I'm not going to do that. I think the elementary nature of this argument speaks for itself. But if you want to get very technical, you can justify that using calculus. So, what is that? Well, this is equal right here to what? Well, this is just equal to 2 log n. 2 log base 2 of n, right? So what am I going to pick for n0? So we're going to choose n0 is equal to 4. Therefore, by the definition of big O, the nth harmonic number is big O of log base 2 of n. And we're done. And that concludes our final example. So this one is far less trivial than the other ones, especially after I showed you that nice general property. So hopefully this helped you out. So this is going to we're going to conclude this big O bootcamp. I hope to do more of these. So do let me know in the comment section what you think, or on whatever platform it might be. Furthermore, if you want the notes for this, so if you're not taking notes with this, or you don't want to just watch it and you want to be able to read it, I have access to these that I'm going to be putting out later today of the written note variant of this bootcamp. It'll be available on Patreon and Subscribestar. So if you donate or contribute to help support me in doing my mission of providing free and accessible computer science educational content, please contribute and help me out, okay? I put a lot of work into this, and I'm hoping that you appreciate what I do. I just do what I do. I really want to help everybody out. That's really what I feel I need to do at this stage. So that being said, do check out those out. And even if you don't really have anything to help contribute and help me out, you're more than welcome to just subscribe to the channel. Let your friends know. Do check out my content. I do have more videos coming out probably in a couple of days. I should have a few more lectures of my advanced data structure series coming out. So hopefully you enjoy those. I want to say thank you very much. And I appreciate very much you reaching out and checking this stuff out. We hopefully had a good time with me. So I want to say thank you very much and have yourself a beautiful day.